Yeah, hello everyone. We start with the interactive segment here. There will be thinking time here, and the Discord has the thread where you can interact with the game, with the problems. Be careful to only post solutions or ideas in spoiler tags. We are happy to answer questions. We'll do it live, test how things work. Hopefully no one will go south. And pen and paper is not necessary. Sometimes it helps to doodle or draw stuff. We will read out the questions in one go, and we'll leave some time to the questions and for thinking afterwards. So let's get right into it.
Okay, so the first question is about a robbery. There are 8 people, A, B, C, D, E, F, G, and H, who are on a trial, and we know that 3 of them committed the robbery, and the rest are innocent. Now, 7 of these 8 people make these statements. Everyone claims that someone else is innocent, and the bottom picture shows who claims about who. And we know that innocent people always tell the truth, but the robbers may either tell the truth or lie. You need to figure out who committed the robbery. You also need to convince me about how many possibilities there are. Maybe there are multiple solutions, or maybe we can know for sure who the 3 robbers are, or maybe there are no solutions at all. So that's part of the question as well.
Question number 2, we write down the powers of 3. So these are numbers of the form 3 times 3 times 3 times 3, any number of times. The first few elements are, for example, 1, 3, 9, 27. And we mark the digits, the digit in the tens place. That is the second digit from the right. These are red in this picture. In the case of 1, 3, and 9, it's 0, then it's 2, 8, 4, and so on. We notice that it seems to be always even in the first few cases. Is it always true, or is it possible that maybe somewhere in the far away it's odd? So this is question number 2. Is this always even?
Question 3, this one has a story. It's about Romeo and Juliet. Romeo really wants to marry Juliet, but Juliet is not that interested. Romeo asks Juliet's hand every week, but she keeps saying no. After some time, Juliet finally says she'll marry him, but only if Romeo manages to win the lottery. So in this lottery, they draw 10 numbers out of 40, and to win, you have to select exactly those numbers in a lottery ticket. It will be too expensive for Romeo to buy enough tickets for all possibilities, so he goes to an oracle. He receives a prophecy that if a number x is drawn, and x is at most 39, then the next number x plus 1 is also drawn. So here, x is not just one concrete number, but this sentence has to be true for every possible x. Okay? Assuming that the prophecy is correct, how many tickets does Romeo need to buy to have a full match and to marry Juliet?
So we have a few more problems that we won't discuss. They are also in the Discord server with spoiler tags. We will show these questions for a bit. They are recorded. They can be viewed back later on, but there's really no point to think about them. The 3 main questions will be discussed. I'm not going to read out these either. They're really just for entertainment if you are quick and done with the other problems. And then after this, we will do a thinking time, probably 15 minutes, and we'll ask any questions in the chat or in the Discord. Here's a summary of the problems in short little bits, just to remind, but the full pictures are in the Discord. And any question that comes up, we are happy to answer now. We will also go back to the questions. We reread them for the late arrivals, but this should be the thinking time.
Also, feel free to work together if you want, but be careful with that. Don't just read someone else's solution by accident. But working in groups is fine.
Oh yeah, and then there's no prize for solving all these problems, so it's just your satisfaction, and you will get a little bit more from the talk if you think about these. If you're watching it live, you're still encouraged to think about the problems, but it's also equally good to figure out later. Yeah, so I guess that should be the introduction, and yeah, we have a little discussion in the Discord, so if a question pops up or a clarification, we are happy to answer.
I see Punky trolling in the chat, saying that he trusts G.
I see some success in the YouTube chat. So yeah, I mean, you know, there's not a requirement to share it with us, but if you have ideas, you can type it in Discord or.
I remember when I first saw the first question, I was like, "Oh my gosh, it's like a complicated knights and knaves thing," but it's actually not, because it's a very simple setup. They're all just saying one thing about the person next to them.
Okay, so we prepared this slide about the hints. It's just like little nudges if you are stuck.
Can I ask a clarifying question here for question 3? So I think I misunderstood it because I took it as like a kind of procedure that would happen, like 10 numbers would get drawn, and then if any of those is less than 39, which they will be, then the ones after it will get drawn, and so you'll end up with more than 10 numbers. But that's not what you mean, right? I think you mean that there will still only be 10 numbers drawn in total.
Yeah, I see. So so the prophecy is very clear. Yeah. If a number is drawn, then the next one is also drawn. The prophecy doesn't say anything about the number of winning.
But there'll never be more than 10 numbers drawn, or am I?
And then the lottery tells you that they only draw 10 numbers.
Okay. Now I need to go away and think about that.
Should we wait a little bit more time, or what's the? I mean, we can also check the YouTube and Discord.
Yes, exactly. As Punky says, there is no clause that says x plus 1 is drawn if and only if less than 10 numbers are drawn. So the prophecy is truly independent of how many numbers are drawn. Yeah, I think we will start the talk soon. We won't discuss the solutions for a few more minutes.
Yeah, there's a little filler bit before the discussion of the solutions, so you can think about it in the back. But yeah, we have lots of slides, so yeah. So welcome everyone. Now that we are done with the interactive bit, you can still think about it in the back. These are not super heavy slides. Let's get a proper introduction. So we are 2 mathematicians from Hungary, currently living in Oxford, the UK. And we loved puzzle games and started working together to make Trifolium, The Adventures of Gary Pretzelneck. My name is Levente. I did my PhD in theoretical computer science here in Oxford. And I work as a researcher in combinatorics.
And my name is Zsombor. I did my PhD in topology, also here in Oxford. And I occasionally teach mathematics with something called the Pósa method.
So we used to participate in these Pósa camps in secondary school. The way we learn mathematics there influenced how we think about puzzle design. And we would like to show you that way of learning mathematics, because it's probably not what you learned or how you learn maths.
So being both mathematicians and puzzle players, we noticed an interesting connection. The way you are taught mathematics is using essentially the same discovery-based method as some puzzle games do. Moreover, math teachers have used that way before it became a design philosophy in puzzle games. So there's a clear parallel between them. And there's a lot of research on education, but much less on puzzle games. So if a lot of smart people spend time figuring that out in math, then we should probably look at their methods to see what we can use in puzzle games. Now, there were at least 2 talks at this ThinkyCon that are somewhat connected to our talk. Glenn talked about a more general theory of guided inquiry curriculum. The Pósa method that we are going to talk about is a small sub-area of that, if I understand it correctly. And Nick also talked about why there is joy in thinking about difficult problems, which is another important point that we also have. So I encourage you to watch both of these talks if you want to get some more context. They are excellent talks.
Yeah, so Hungary has a very long maths problem-solving tradition. For over 100 years, people spend time thinking about and improving maths education. The outstanding figures are included in this picture. Probably there's not enough time to talk about them, but they all did excellent stuff. I just wanted to make a note that we wouldn't be here without their ideas and contributions. Kemal here is a monthly magazine for secondary school students. It contains fun maths problems to think about. And George Pósa wrote a famous book called How to Solve It, about general problem-solving ideas. It wasn't just about mathematics or restricted to mathematics.
Okay, chapter 2, the Pósa method. So to understand the Pósa method, let's first look at the usual way of teaching maths. The usual way is that the teacher gives a piece of theory, a sort of lecture. For example, whenever you see an equation like this, ax squared plus bx plus c equals 0, then you can solve it using this formula. Then the students practice using this formula in several problems in the class and in homework. Now, unfortunately, this is what most people think of when hearing the word mathematics. Solving equations, plugging numbers into formulas, the solution is 7 and everyone claps. But this is not at all what real mathematics is. No mathematician is clapping because we got that the solution is 7. The students didn't really learn anything interesting. The main problem with this method is that if the teacher tells the students how to think, then they won't be able to learn how to think. The teacher deprives students of the joy of thinking. Here's a quote from Pósa that I think captures well what the problem is with this mode of teaching. There are children who grow up without ever experiencing what it's like to feel, here's a problem and I can think about it however I want. So here's a better way of teaching this topic. Again, mathematics is not about solving equations, and so this is not even a topic in the Pósa camps, but I want to show you that even this mundane topic can be taught in a way that focuses more on ideas, because there actually is a quite clever idea behind the quadratic formula. So in this method, I don't say anything, I don't tell you the quadratic formula. Instead, I give you a sequence of problems that guide you into certain ideas. The first problem is solving x squared equals 5. That is finding all real numbers whose square is 5. You can probably solve that. The answer is the square root of 5, because that's the definition of the square root, or minus square root of 5. If you haven't seen before that this type of equation has 2 solutions, one positive and one negative, then this is already a new idea. So this first problem just focuses on fully understanding that. Then the second question is x minus 3 squared is 5. How can you solve that without knowing the quadratic formula? I'll wait a few seconds. So the trick is that you use the previous problem. We know that if the square of something is 5, then that something is square root of 5 or minus square root of 5. So in this case, x minus 3 is plus or minus square root of 5. And we have solved the equation because that means that x is 3 plus or minus square root of 5. Okay, I won't go through the whole sequence, but I'll just say that every question is just a tiny bit harder than the previous question. contains just one extra small idea or small step. The problems build on each other, so in the third question we use our understanding of the first two questions. And by the end of question 7, you will essentially come up with the quadratic formula yourself. Here's another quote from Pósa. In traditional teaching, things that aren't properly understood just fade away. But when students discover many things on their own, those stay with them much longer.
So the main goal of the Pósa method is that we want the students to enjoy doing mathematics, to be happy while thinking about interesting problems, and to experience the joy of thinking. We want them to discover mathematical concepts and ideas themselves. We let students think about the problems for a really long time, so that as many people can figure them out as possible. And we want to teach them how to think more efficiently. And it's not just about mathematics. Thinking is something that is universally useful.
Okay, time is up. We need to discuss the solutions to the first 3 problems. If you wish to think about them some more, feel free to pause the video and continue watching later. Question 1, robbers. We asked in the hint, what happens if A is innocent? Well, if A is innocent, then A is telling the truth, which means that B is innocent. But if B is innocent, then B is telling the truth, and so C is innocent. And then D is innocent. There is a chain reaction. Everyone is innocent, which cannot happen. This means that A cannot be innocent. What if, for example, C is innocent? Then again, there is a chain reaction starting from C, and we again see that there are too many innocent people. So C cannot be innocent either. Similarly, B cannot be innocent, which means that we found the 3 robbers, A, B, and C. The rest must be innocent, and you can check that this configuration works. Innocent people indeed tell the truth, robbers either lie or tell the truth. And we also showed that this is the only possibility. Okay.
So question 2, powers of 3. As an example, let's see what happens when we multiply 243 by 3. So the 10th digit is 4, it's even, and if we multiply it by 3, an even digit times 3 is still even. Let's see the carry. So we have the unit digit is 3, and if we multiply it by 3, we get 9. So there is no carry. It doesn't affect the 10th digit, so it remains even. The situation is slightly different at 729. Here, 9 times 3 is 27, so we have a carry, which is 2. But luckily, 2 is even. In fact, you can check that the powers of 3 can only end in 1, 3, 7, or 9. It would cause trouble if it ended in 5, but this never happens because powers of 3 are not divisible by 5. So because of this, whenever a carry occurs, it is always 0 or 2 coming from the 1, 3, 7, and 9 ending, and they are both even. Therefore, if the 10th digit is even for one power of 3, then it remains even for the next, and for the next, and for the next, and so on, which means that the 10th digit is even for all powers of 3.
Okay, question 3, lottery. Let's see, for example, what happens if 28 is a drawn number. Using the prophecy for x equals 28, we then know that 29 is also drawn. But then using the prophecy for x equals 29, we know that 30 is drawn too. And then 31 and 32 and so on. It goes up until 40. It doesn't stop at 37, that's when we would have 10 drawn numbers, but the prophecy still must be true for x equals 37, so 38 must be drawn too. So the structure of the thing is that the drawn numbers are the numbers between something and 40. Since we know that there are 10 numbers drawn, it means the only possibility is from 31 to 40. So Romeo buys just one ticket. Okay.
An important concept in the Pósa method is a problem thread. So the connections between the problems are much more important than the individual problems themselves. The connection can be any separable element of thinking, for example, an idea, a method, or a type of mental representation. And the collection of several connected problems is called a thread. This is a collection, so the problems might not have a completely fixed order, though there usually is at least an approximate ordering that makes sense. These threads are what trigger the discovery learning process. This talk is titled Designing for Discovery. So to understand how to design for discovery, we need to understand the threads. These definitions are a bit abstract, perhaps, so let's look at some examples.
So we've already seen an example of a thread, the sequence about quadratic equations. These problems build on each other. Problem 7 would have been too hard on its own, so we separated all the little ideas into separate problems. So that will be our definition for the first type of a thread. An idea thread is when an observation, subproblem, or lemma is separated into its own problem that can be used in later problems. If the thread is long enough, it can build up an entire area of mathematics. And for those of you who looked at some of the extra problems, you might find more examples of an idea connection there. So,
so question 3 and question 4 is an example. Now, what about these problems? The 3 main problems whose solutions we just discussed. What's the connection? Feel free to answer in the YouTube chat. I think I saw someone actually mentioning it. So they might look like they have nothing in common. The first problem is a logic puzzle about true or false statements. The second is some kind of number theory problem. And the third is about minimizing the number of lottery tickets. They look very distant, but there is a connection. So someone mentioned induction, but we just call it chain reaction. The solutions are all about chain reaction. In question 1, someone is innocent, triggers a reaction, and everyone after it is innocent. In question 2, if it's true for 1 power of 3, then the chain reaction starts and everything after is true. And the same in question 3. So if a number is drawn, then everything after it is drawn up to 40, of course. So the method of solving all these were the same, but in different contexts.
So this is what we call thread type 2 method, teaching a general method or tool to solve problems or a way to think about problems. So an important difference to the previous thread type is that the method can be used in different contexts, and the thread of problems shows that. For example, proof by chain reaction was used in 3 very different problems. And by the way, mathematicians like to call it proof by induction, which is one of the main ways of proving statements. So chain reaction is a very important idea. I've put some more examples on these slides just to show you that these are not the usual types of mathematical techniques that you might think of. We are not talking about integration by parts, which is a method for computing certain integrals. We are talking about general methods and ways of thinking. For example, movement is a certain method that can be used in a geometry problem or an algebra problem or a combinatorics problem. It can also be a mindset or just a way to start thinking about a problem. As puzzle players, we are probably used to experimentation. What if A is innocent in question 1? Most of you probably start experimenting with it. But since I can't be sure that you know this method of experimentation, I gave you that hint in question 1. Can A be innocent? So this guides you towards experimenting. We are teaching not only, and not even primarily, the fields of mathematics, but the art of thinking itself. And in this, developing an awareness of the possible ways of thinking is of great importance. So we are using the different mathematical areas only as a tool to teach you about the ways of thinking that can be used across these different areas.
So the thread type number 3 is abstraction. This is about building familiarity with an abstract concept. We do this by giving more and more abstract representations in problems that help to build a more abstract mental model. For example, if we look at these problems again, you might notice that they are getting more and more abstract. To see some more examples, it can be any mathematical object. Building familiarity means learning to think in terms of the new mathematical object. For example, when teaching graphs, the first problem might be about cities, roads. The second problem might be about a group of people and friendships between pairs of people. The third problem is about islands and bridges between them in the picture. After a few problems, you might realize that the common structure in these problems are graphs, which is the picture on the right. It has some vertices, some edges between them, and you might find it easier to think about these problems in terms of graphs. So when you see this picture about bridges, you're first turning to the image on the right. You replace the island with small points. You replace the bridges with edges between the points. In other words, you're doing abstraction. Another example is understanding space geometry. So developing a mental image for 3 dimension. If you imagine a sphere and a slanted plane intersecting, what's the intersection? Do you see it in your mind that it's a circle? Can you rotate a 3D object in your head and visualize how it's rotating? People who play 3D video games usually develop a mental image for that, but that's something that you didn't always have. Or the concept of proof comes up in mathematics. What does it mean to prove something precisely? What's the difference between a convincing argument and the proof? That is something that we need to learn in mathematics. Or the concept of impossibility. What does it mean to be impossible? You check the first 1,000 cases, for example, the first 1,000 powers of 3, and they all happen to be even in the 10th digit. Does that mean that it's impossible for all cases? How do I prove that something is impossible?
Okay, so we talked about threads. We've seen different types of threads, but we haven't explicitly said a very important thing about threads. In this picture, every line represents a thread, with the dots being the individual problems. And mathematics is not like this. The threads are not separated. Mathematics looks much more like this.
Threads regularly cross each other at problems. Problems belonging to these crossing threads, forming this thing called a web of problem threads. We can go.
Yeah. So there are hidden connections. There are moments of surprise that arises when 2 threads connect, for example. And it also teaches the pick from toolbox skill.
So in both mathematics and the real world, problems don't come with tutorials or thematic regions. So running multiple problem threads in parallel helps discourage the unproductive habit of thinking, we are learning technique X, so how can I apply technique X in this problem? This mindset has little value outside these artificial testing environments.
This quote is from Zoltán János, a former student of Pósa, now a teacher. We are building in the children's head. It's a nice way to phrase it, but we are not building up the theory on the blackboard, but in the children's head.
So what is the teacher's role in the Pósa method? With Pósa's words, the goal of the method is to have as many students as possible to discover as many things as possible. Some discoveries could be hidden behind hard ideas, advanced methods, or abstract concepts. Recall the thread types we mentioned. The goal is to advance these skills in these threads through a carefully curated problem sequence. So the teacher should build up a foundation in the student's head, and then when they encounter the next challenge, they have all the tools needed to solve it, and the success feels self-made. more memorable and stays with them longer.
They experience it as there were interesting problems and I was able to solve them. They don't necessarily see it, and they don't need to see that the reason they could do it was that their teacher had, through earlier problems, quietly taught them certain things.
So we have a few details about the camp. Included here pictures as well.
We will skip them.
We will skip because of the time, but this is how it looks like usually.
Okay, now that we understand the core principles of the Pósa method and have seen some examples, we can finally talk about why it's relevant to puzzle design and what puzzle designers can learn from the Pósa method. Because it seems to me that two entirely different groups of people, mathematicians and puzzle designers, invented essentially the same thing independently from each other. So understanding the Pósa method gives a nice framework for thinking about puzzle design.
So there is an obvious parallel. Thinky games and the Pósa method share the same goal, to make thinking enjoyable. There's also this Csikszentmihalyi's flow theory. So you ideally want to maintain the flow, always the right level of challenge. So the discovery method is useful in both contexts. You want to maximize the discovery both in puzzle games so that the ideas stay there longer. For the teacher, in the discovery method and the puzzle game designer, they play similar roles. They create a sequence of challenges in order to advance the players or the students' understanding and skill. There's a non-verbal problem and sequence-based communication of these really, really complex ideas and problem-solving skills. And it's also very important why we compare it with mathematics is because it's accessible. Unlike researching the DNA or an ant colony, it is really easy to just think about Romeo and Juliet's lottery tickets. You don't need anything. There's also this slide, the differences. We briefly you can see. I added these little stickers to indicate different types of thinking activities and the teaching, but I just quickly skip through how they are placed on this scale. It's very subjective. I just placed them how I felt at the moment, so shouldn't be any significance attributed to this.
Okay, now let's look at threads. Thread type 1 idea is when a certain idea or lemma is separated into its own problem that can be used later. This seems to be by far the most used thread type in puzzle games. A tutorial puzzle teaches you something, a mechanic, a rule, an interaction, an idea, and then later puzzles use that. You can teach lemmas, you can prepare the player for a hard puzzle by teaching a useful trick in a simpler puzzle first. Or the next puzzle looks similar to the previous one, but has a twist, a slight modification makes it so that the easy solution doesn't work anymore. So the question is, why is it most often this type that's present in puzzle games? Can we make games with the other thread types?
So thread type number 2, the method, is when the collection of problems teaches you a method of solving or a way of thinking. This is very rare in puzzle games, but Islands of Insight has a very interesting example. In that game, there are logic grids where you have to color every cell black or white based on certain rules. Now, experienced puzzle players know the method of deduction. You know something for sure, you mark that cell, and if you don't know for sure, you don't mark that cell. However, beginner players won't necessarily use this method. They might just quickly color over the squares, then try to fiddle with the colors until all the rules are satisfied. Just trying random stuff until it works. People who play this way will eventually hit a ceiling and won't understand how to get any better. So Islands of Insight has a brilliant way to teach the method of deduction. One of the possible rules is underclued grid. This means that the puzzle has multiple solutions, and your task is to color only those cells that you know for sure. So the player can't really guess the solution. They must make a series of deductions instead. After solving some puzzles of this type, players will start to get a feel for it and understand the method of deduction. Moreover, they might realize that this method can also be used in puzzles which are not under grids, where you have to fill out every empty cell.
Threat type 3, abstraction. This is when problems build familiarity with an abstract concept or mental representation. This type is again less used in puzzle games. Most games are not that abstract. You see things on the screen, you manipulate them, you see the result, and you don't have to develop a mental representation. But knowing about this type can be helpful too. Sometimes you don't just have to build on ideas, you also have to build familiarity with something. So here's an example from our demo for Trifolium. It's a 3-dimensional game, and so we have to be careful about building familiarity with 3-dimensional space. Someone complained about not understanding why this is not a solution to this puzzle, and it's not their fault. I think the problem here was that we ran too quickly from mostly 2D puzzles to this very 3-dimensional puzzle in the demo. As any abstract mental model, 3-dimensional understanding should be built gradually in small steps. We can do that in the full game, but since it was a demo, we skipped a few puzzles to showcase something really 3-dimensional. So that's a useful way for me to think about puzzle design and understanding why some players have certain issues. You don't just build on ideas, you also build familiarity with the game.
So let's talk about hints. Can of Wormholes is probably the closest to the Pósa method in terms of how it gives hints. In that game, you are stuck on a level, you can click Gain Insight, which will give you another puzzle, for example, the image on the right. A simple puzzle that guides you to the same idea that you need in the original puzzle, but with much less complexity. And this is great. Can of Wormholes revolutionized hint systems in puzzle games. Many other games follow this method. Now, this is very similar to the Pósa method, where hints can take the form of a helpful question or a helpful problem. Instead of giving away the idea of the original maths problem, we can ask, can you solve this easier problem? Remember, we want to give the smallest possible hint that gets you over the hurdle. Of course, it's much easier in teaching, where you can talk to the student and you can figure out what the best hint is interactively. In puzzle games, the feedback to the designer is much smaller, and so it's hard to prepare for every possible scenario. But it's not just about helping when you can't figure it out. It's about helping through building. The point of this building is that by the time a student encounters a problem, what they need to solve it is already present in their mind. And if that's still not enough, then of course we can help further. But that's not where it starts. It starts with building up the material. So these are two important concepts to keep in mind if you want to copy this kind of hint system in your game. Also, this kind of wormholes example, I'm not sure if it's the smallest possible hint. It's very forcing. You literally can't avoid doing the trick. And maybe that's fine. Maybe people who clicked on the hint already gave up and just wanted to be told the solution. This often happens in the Pósa camps too. In the beginning, students want to get to the solution quickly. After thinking for a while, if it didn't work, they would want to help. However, after a few camps, the situation changes and they start to understand the joy of figuring things out on their own.
Eventually, and this even becomes typical, they no longer want me to help. They don't want to discuss the problem. Again and again they ask, not yet, I still want to think. So,
An often heard puzzle design advice is that areas should have a clear theme, for example, exploring a certain mechanic. But there is value in being able to select the correct tool from your mental toolbox too. In maths, realizing an unexpected connection between two problems is exciting. Both ways of structuring puzzle games are valid, and anything on the spectrum can work. However, in the Pósa camps, there are always at least two different threads going on at the same time. You can choose which problems to think about, and you need to make the connection that this problem is related to the other problem, and you can use the same idea.
So you don't necessarily have to lay everything out ready-made in front of the students. part of the adventure of thinking is realizing along the way what you need and then working it out. That too is a valid way of building. I think we need to skip a few slides because time is running out.
Okay, so yeah, this was mentioned in another talk. So
I think I want to close with this quote because I really like it. We want children to think, to wrestle with problems, to experience what it's like to think freely, to get lost, to be in the dark, to find the path, to reach the goal. Oops.
Yeah, so we had an exercise, but we ran out of time. So probably we just end here. The links on this page should provide more detailed information about the camps, the problem threads, and the Pósa method. We hope you enjoyed, learned something new.
Yeah, that's it. Thank you.
And yeah, let me know if you have any questions, if we have time.
Thank you both. Yeah, we absolutely have time for questions. That was a great talk. Thank you so much. And we did get some questions in the chat as well. And I've asked in case there's any more questions to come through. In fact, one just came through, which is great. I might prioritize it over the joke questions that came up as well, but we'll see. Actually, the first thing that I noted down as a question wasn't a question, but I thought it's actually an interesting one, which is that Plush Lawless made a comment saying, in my experience, it is teachers that have a lot to learn from puzzle games. Whereas like part of the message of this is the puzzle games have a lot to learn from how maths can be taught. What are your thoughts on that and teachers learning from puzzle games? Because I guess that ties into what Nick Chen is doing with playmath.org, as he talked about in yesterday's talk.
Yeah, so I think so the Pósa method was designed for above average students, and even he mentioned that it doesn't really work in every context, because there are kids who never experience thinking. You can give them a problem and they don't know what to do with this. They never had this feeling of, and there's also this problem of failing. I had a slide about it, but it skipped. So in the classroom, what you see is that there's a problem, like in a typical way of teaching, there's a problem, and then the teacher immediately, after 5 seconds, writes out the solution. And it doesn't really, encourage you to think, to spend time about these things. So what, for example, people do is, in puzzle games, it's perfectly fine to think about one puzzle for 5, 10, 15 minutes. I mean, for example, I think about one problem for months. That's my job. It's really there's a massive gap, and I mean, I guess teachers they have to cater to a lot of people, but with Pósa he could choose what he works with.
I suppose that's why you gave us 3 problems to think about at once, right? Just in case we got stuck on one, we could think about another one at the same time.
Yeah, and then the point with the problems is we wanted to provide the same experience, that if you interact with something, then it becomes more memorable.
Yeah, and as we noticed, people in the chat were identifying the connection between them, even though you hadn't explicitly stated that in advance.
Yeah.
So next question, I'll vary the people who are asking. So Feverish asked this question, which is, when is there too much of a gap where you shouldn't expect someone to be able to make that next intuitive step? How do you know what is too hard to figure out?
I mean, that's probably the biggest challenge in education.
I guess they were probably talking about the point where you had problem 1, problem 2 down to problem 7, and it was to do with the quadratic equations. How do you know whether your steps between the problems are too big, or maybe even too small in some cases?
Yeah. So I think this is one of the advantages of education, that you can just ask, what do you think? Where are you stuck?
Yeah.
And then it's a hard challenge to figure out that what's going on in their heads, and then adding the proper minimal nudge. So in this example, you want to keep them in the flow state. You don't want to frustrate them, or so you ideally want to give a hint at the moment. It would
just as they're about to leave that zone. Yeah.
Yeah, exactly. And then the one thing I wanted to mention in this is that so this challenge is not just one direction. So we mentioned a few thread types. For every thread, you could have a challenge. So a problem might be too difficult because it's too abstract. It might be too difficult because it's some idea is missing. So it's very hard to. It's also a challenge to figure out what's missing.
Great, thank you. So then a question here from Patrick Trainer, which is, how can we balance wanting players to search for the correct tool in the toolbox versus providing structure so sequencing and game progression / narrative doesn't feel random and chaotic? Interesting. So I think, yes, you talked about how you can mix things up a bit more, so players have to try and find the right tool in the toolbox, but balancing that against structuring a game.
I mean, I have something to say about it.
Yeah, I mean, maybe what often happens in the Pósa camps is that there are 2 threads in parallel, for example. So it's not like there is no like absolute freedom of what connects to what, but there's just 2 different threads that might make it easier. Maybe.
I guess that's interesting, because that reminds me of like a common structure I've seen in puzzle games is I've literally just seen it in Spooky Express. The game branches. You have one area that's about one kind of thing, one area that's about another thing, and then they come back together, and then you're expected to use those 2 things that you've learned. I guess that's one way of having like 2 threads running alongside each other. Although I guess usually in that situation, that both of those threads are going to come up in every single puzzle in the join place, but maybe it's worth exploring, like what if they don't both come up and you're expected to find.
Yeah, and then if I add something to that, so I think it's also like it's a type of skill to know that you have you encounter a problem and then you think you intuitively figure out what sort of tool you need. So this is a very specific skill that you can actually improve and build a thread on. So in the Pósa camp, there are sometimes just 2 threads, but it builds up gradually, and then maybe at the end of it's like a 6-year process. Maybe at the end of the 6 years, you might have 4 threads. Maybe something comes up from 2 years ago. Like it's also something to build up gradually.
Absolutely. All right, we will leave that there. Thanks, everyone. Thanks, you two, for presenting that. It was excellent. We will head over to the next talk. And thank you both again.
Thank you very much.
Thank you.